In this short video, we're going to do some HVAC simulations where we look at the heat transfer from our radiator into the room of a domestic house. So first of all, just grab Ansys CFX and drag it into the workspace. And right click on geometry and hit new design model geometry. And once that's loaded up, we're just going to create the outline of a room by selecting the XY plane and creating a new sketch beginning at the origin. So just approximate the shape of a rectangular room by making sure the cursor is or has that point logo, and then expand out to approximate the size of a domestic room. So here that's probably more than large enough. I'm going to extrude this sketch by 3.5 meters. So just making sure we've added material, it's fixed extent, it's normal, and we'll go 3.5 and hit generate. Once you've done that, hold the middle mouse button and just have a little rotate. Right, so that's the general shape of the room that I'm interested in. Another thing I'm interested in is the recess of the window, and that window in the room I'm interested in exists here. So what we need to do is view the negative x-axis, and we need to create a sketch somewhere here. So looking at this, this is the YZ plane, and just creating a sketch there, selecting the sketch, and again just creating another rectangle. Don't need to be too accurate, this is just for demonstration purposes. It's quite a large window and it sits approximately there. Because the window is recessed, it's going to be this is going to be extruded in the negative x direction. So again, just hitting extrude. We're adding material. It's only a small recess, it's about 0.2 meters. Just need to have a little look and see which direction this is going in. So as you can see, it's extruding into the domain. We don't want that. When it's out of the domain, I'm just going to hit reversed, and there you can see the preview here is reversed away from the room. And that's suitable, so we can just hit generate there. And finally, there is a radiator that sits underneath the window inside the room. So we have to do something a little bit different here. You have to create another plane off this ZY plane that sits inside the domain, and then extrude the radiator into that. So just again, viewing this negative x direction, looking at this YZ plane, and creating another plane from it. It needs to be transformed into the positive x direction, but just to be sure, I'm going to use the global x, just to make sure that just say that, because it's slightly hidden here. And it's very close, so it's going to be in the order of 0.1 meters. I'm going to have to slightly exaggerate this, just so we don't get any issues with meshing between the radiator and the wall. But just performing that, that should give me a plane there. And then finally, I can perform a sketch on that plane. It's just a simple rectangle that sits inside the computational domain. And then we're going to cut that away from the room. So the radiator sits just below the window. It's quite large. We can say it's about there. Right, so we have a sketch, and just hit the extrude button. Make sure it's appropriate It's hit sketch 3, good. Rather than adding material, we're now going to go through the process of cutting. And I'm going to say it's about 0.12 meters deep. And again, just look for that preview, see where the preview goes. Preview goes into the domain. So that looks about right. So just hitting generate there. So for this simple case, that will be suitable. I'm going to make one more addition to this domain. I'm going to note the presence of the door, which sits approximately here. So just viewing this from the positive X direction now, the opposite end of the room. And I'm going to create a plane, and it's going to sit on the surface. And it's this surface here, like so. So just hitting generate there. Finally, I'm just going to create a sketch. Which will be sketch 4. Create a rectangle. Which represents the presence of the door there. Again, not being too accurate, just getting an approximate shape. This time when I hit extrude, I'm not looking to apply material at all, I'm looking to just imprint faces. So all this will do is create the shape of the door on the outside of the domain, and because of that, I'll have a separate boundary that I can apply a different temperature boundary condition to. So before you go any further, make sure you hit save, and if you haven't already done so, save your project. So once you've done that, move on to your meshing. So now meshing software is open, we can just give the domain a little rotate and just review it again. So what we're looking to do is simulate the heat transfer from a radiator that exists here that you can't quite see, and we're going to model the effects of things like the window and the door. So I'm just going to begin with a default mesh just to see how it presents, and as you can see it's relatively coarse. So I'm going to go through things like default element sizes of maybe 0.2 meters and see the effect of this. That's a lot more reasonable, and in places like the window I'm going to perform some extra refinement. So just doing things like selecting the faces for the window and the edges of the window edge, and right click on mesh, insert, and we're just going to refine these so they're in the order of 5 centimeters rather than 20 centimeters. Okay, that's much better. And then finally, just fit that to view. We're going to perform some more refinement on our radiator. So we need to find the radiator in this domain, and we know it sits somewhere down here. So if we do that, we've picked up all the faces there. And again, just going in the order of 5 centimeters there. We can go a little bit further and add prism layer cells to the radiator, because we need to make sure we're capturing that heat transfer. So prism layers sit under this inflation option. So our geometry, First of all is the entire computational domain, and the boundaries we're interested in are those of the radiator. So somewhere here, just making sure we capture the total thickness as quite a small number, because remember that we've only got a small gap between the radiator and the outside wall. I'm going to put this in the order of 3 centimeters, still quite large, but this is more demonstration than complete accuracy. Alright, so that's meshed. I'm just going to cut this down the center line so you can have a bit of a look. So just selecting section plane and dragging this all the way through the middle. You should see cut off here, and just rotating and fitting to view. What you should see is quite a fine mesh around the radiator and the window, which then coarsens out throughout the room. Just zoom in a little bit more on that. So as you can see, the prism layer cells are there. Right, so once you're done with that, save and open CFX. Before you do, just make sure you right click and update the mesh. So in Ansys CFX, you can see the computational domain that we've previously meshed. So you can see the presence of the door, the window recess, and the radiator. So we're going to start by assigning boundary conditions. And we'll be a little liberal here and assume that all the walls and the floor have the same behavior, and then just treat the window and the door slightly differently. So calling this one walls, just selecting the various surfaces. So just holding control to do this, remembering that the edges of the window are going to have slightly different behavior. So once all they're selected, we know that it's a solid no-slip wall. So we can just hit apply and close. I'm then going to add the door, which in this instance I'm going to leave as an outlet. And just assuming a relative pressure of 0. Of course, we can have the window. It's not actually going to be an open window, it's still going to be a wall, but it's going to be given some heat transfer behavior in a minute. Again, just no slip, smooth wall. So if we've selected everything correctly, the final boundary condition will just be this radiator. So rather than doing anything here, I'm just going to call that radiator. So what we need to do now is just go from the top, work down, and set the analysis type and boundary conditions. So I'm actually going to make this a transient simulation and begin with a total time of 60 seconds, time step of, let's say, 0.1, an initial time of 0 seconds. What we're being told here is we need to add some more conditions in order to make this simulation work. So we'll just close this. In default domain, we've got air. It's a continuous fluid. It's going to be considered buoyant in this case, and our gravitational acceleration is minus 9.81 meters per second squared, with our reference temperature being 25 degrees Celsius. What we also need to do is ensure it's not an isothermal simulation, but we include thermal energy. And I'm going to leave these terms alone for the moment, and also leave our default turbulence model as K epsilon. We need to initialize the simulation because this is transient, so we need to take our values from somewhere. So just setting initial velocities as 0 and relative static pressure as 0 and temperature 25 degrees Celsius. We're going to assume very low turbulence intensity, and now we should receive some complaints about our boundary conditions. So our door is being considered an outlet. We have a radiator where we've got no slip, smooth wall, but rather than being adiabatic, we're going to assume a constant fixed temperature of 80 degrees Celsius. Our walls, we have several choices. So we can assume a heat transfer coefficient of, let's say, 10 watts per meter squared per Kelvin with an outside temperature of 12 degrees Celsius. And the window can give that slightly higher heat transfer coefficient. So let's give that a 50 with the outside temperature of 12 degrees Celsius. So just running into solver control. I'm going to leave the current number alone for the moment. We leave our limits of the current number alone. You can leave most of these as default. But what we are interested in is this output control here. So transient results. So we want to receive these transient results every 1 second. So just apply. So once you've done that, just hit Save Project. And then shut this down and we'll open up solver control. So just hitting double precision, large problem, and I've got 4 processors I can use here. So I'm just going to hit run. So when your simulation's finished, just double click results and give it a moment to load. Okay, so in our computational domain, we've got our window, radiator and door. Just rotate that to a suitable angle. So there's a number of ways we can visualize this. We might as well just begin with a cut plane from the side view. So selecting a plane, we want it in the ZX plane. And if we just use this blue bar, we can move it halfway along and that'll cut the plane down the center of that axis, or approximately so. There you go, you can see the radiator's been cut out. And if we just colour that by variable and select our variable to be temperature. If we just hit apply, you can see we've got our radiator, our cooling walls, and our window here. So what we'll just do is, if we go to animation and select time step animation, just going to hit play and see what happens. So from the radiator, we've got that initial hot air rising up, being drawn towards the window, following along the ceiling of the building, and actually there's relatively little change throughout the domain over the course of the simulation. So another piece of analysis we can do that's quite insightful is volume rendering. So just selecting volume rendering at the top, changing the variable to be temperature, and changing user specified values to be 298 and 305. If we just hit apply there, give it a few seconds, select the time stepping option for the animation, bring that right back to the beginning, and then what you can do is save movie here and just select a file location. So if you just hit play on that, you can save the animation to your computer and obviously visualize it while it's running as well. Just note it might be relatively intensive compared to previous types of animations you might have done, just because volume rendering is a relatively RAM intensive process. So just viewing the result, you can see the way the flow behaves, and although it's relatively quick, it does give you some idea of what's physically happening in the simulation. And if you found this video useful, please like and subscribe to the channel, because this helps us reach more people. Thanks for watching.